All right, so we know that our initial velocity is 55 kilometers per hour. That's the speed limit, but we're going to assume we're traveling at the speed limit. And our acceleration is given, our maximum acceleration is given as negative 5.18 meters per second squared. So the first thing I notice about this problem is that my distance and time up here for the speed are in kilometers and hours, but my units for acceleration are in meters and seconds. So I'm going to convert my velocity to a new velocity using meters per second. So I use my conversion factors just like you used to do in chemistry class. As long as you multiply by something that is the same in the numerator and the denominator, that's like multiplying it by the number 1. So 1 hour is the same thing as 3,600 seconds. So this is in effect the number 1. And 1,000 meters is the same thing as 1 kilometer. So the result is this kilometers cancels off with this kilometers, this hours cancels off with this hours, and I'm left with meters per second. So 55 kilometers per hour is the same thing as 15.28 meters per second. Okay, it tells me in the problem that my reaction time, the time it takes to put on the brakes from when I see the light turn yellow, is 0.75 seconds. So of course, while my foot is moving from the gas pedal to the brake, the car is still moving along at the same speed of 15.28 meters per second. So the distance traveled during that time is the velocity times the time for a distance of 11.46 meters. Now where did this equation come from? Well, if you look at your equations of motion, here, if I'm moving at constant velocity, I know my acceleration is 0. So this term completely goes away, and I'm just left with distance is equal to velocity times time. So for things with constant velocity, I can use this much simplified equation. And if you forget, you can always do a unit check. Velocity in meters per second times time in seconds does give me meters. So that's one way to help you remember, if you remembered an equation correctly, is see if the units work out. And they do. Okay, so I've traveled 11.46 meters by the time my foot begins to engage the brake. So no longer am I 40 meters to the intersection, but now I'm 11.46 meters closer. So now I only have 28.54 meters to stop my car in before the intersection during the braking phase. So I've chosen this equation. I know the final velocity is 0. I know the initial velocity is 15.28. And you got to think a little bit here. The acceleration, the maximum acceleration is negative 5.18, and the distance I have to stop in is 28.54 meters. But those two numbers don't go into the same equation at the same time. How come? Well, because I don't know that an acceleration of 5.18 is going to stop my car in 28.54 meters. So what I have to do is I have to choose one or the other. So here I've chosen the distance to the intersection and solved for A. And I see that the value of A I need going this speed to stop in 28.54 meters is negative 4.09 meters per second squared. And that is less than the maximum amount that my car can provide. So this tells me that yes, I will be able to stop in time. However, if I had chosen to use my maximum acceleration and solve for D, I still could have come up with the answer, because if I use my maximum deceleration, I see that my car will stop in 22.54 meters, which is less than the distance to the intersection. So either way tells me that I can stop in time. What if, though, I had decided to keep going and not put on the brakes? Would I have made it through the intersection? And so if I'm moving at the same velocity, of course I use the simplified equation. Distance is equal to velocity times time. So the light is yellow for 2.8 seconds. So this is how far I will travel during that 2.8 seconds. And we see that that number is larger than the 40 meters it was to the intersection from when the light first turned yellow. So I will have traveled far enough to be in the intersection when the light turns red. So I'm good. I could have either continued or stopped, and I would have been fine in either situation. Let's look at part B now that says, now we have a shorter distance to the intersection when the light turns yellow, and the duration of the yellow light is less time. It's 1.8 seconds. I'm still going the same initial speed. My car still is capable of only this much deceleration. But now I'm going to be trying to stop my car in 20.5 meters. So I'm going to use the same method as before. I'm going to first choose the distance to the intersection, 20.54, and I'm going to figure out what acceleration I need to stop in this distance when I'm initially moving at this speed. And the answer I come up with shows me a value for acceleration which is larger in magnitude than the maximum that my car can supply. And if you had chosen to do it the other way, where you say, I'm going to use my maximum deceleration and figure out how much distance it takes me to stop, then I see that that number, 22.53, is larger than the available distance I have to work with to the intersection of 20.54. So either way tells me that no, I can't stop in time. Fine. What if I keep going and I don't put on the brakes? Now I'll be traveling at 15.28 meters per second for the entire 1.8 seconds of the yellow light, which will carry me 27.5 meters. Uh-oh, the intersection is 32 meters away. So I will not be there yet when the light turns red, and I will end up running the red light. So the duration of the yellow light for this speed limit of 15.28 meters per second is inappropriate. The traffic engineer who designed this light needs to go back to the drawing board and figure out a better time or a longer time for the yellow duration. Okay, so in this problem, if we look at the 5 variables that we find in our equations of motion, we notice that we appear to have a value for all 5 of them. Our initial velocity is 15.28 meters per second. Our final velocity is 0. Our maximum acceleration is negative 5.18 meters per second squared. The time before the light turns red is 2.05 seconds. And the displacement or the distance that we have to stop in is 28.54 meters. So we really have to be careful about what numbers we plug into the equation. We showed already that when we use this equation, we chose the maximum deceleration and then found out what the associated displacement is with that acceleration. Or we plugged in the distance we had to the intersection and found out what acceleration we needed to do that, and then compared it to the maximum acceleration. What if we chose to use some of the other equations of motion? Let's take a look at this one first. V final equals V initial plus acceleration times time. If I plug in my final velocity of 0, my initial velocity of 15.28, and my acceleration of negative 5.18, and solve for t, what we get is 2.95 seconds. And that is a bigger number than what we were hoping to have of 2.05 seconds. But be careful, this is misleading. Yes, it will take us 2.95 seconds to stop, but nowhere in this equation do we have displacement. If you think about what the true requirement of this problem is, the true requirement is that we go from an initial velocity of 15.28 to a final velocity of 0 in a distance of 28.54 meters. That's really all that matters. Here what we're seeing is we're going to stop after the light turns red. but we won't have traveled into the intersection. So even though the car is still moving when the light turns red, we do end up stopping before the intersection, and that's what we showed when we used this equation. In fact, we can show you if we use 2.95 seconds, here it is, I'm going to use 2.95 seconds. I have to use another equation to figure out what the displacement is, and you can see here that it agrees now with what I got in part A when I found out that it's going to take me 22.54 meters to stop. And that's using my maximum acceleration, which is what I used right here. You can see 5.18. Okay, so got to be careful. What if I used this equation right here? So again, I plug in 15.28 for my initial velocity, 0 for final, and now I'm plugging in the maximum distance that I have to stop, 28.54, and I come up with a time of 3.74 seconds. So all this is telling me is that yes, I can stop in this distance, going this speed, and this is how much time it will take, but be careful, you haven't verified that the acceleration is going to be less than 5.18 meters per second squared. Nowhere in this equation is there an A. So you don't know if you fit the criteria that you are within you're under your maximum acceleration. So just to show you that you can try it, if I use 3.74 seconds and I can solve for the acceleration, and just like we saw in part A when we solved it the first time, we had an acceleration of 4.09, which is less than 5.18. But we had to verify that with a second step. That did not, we weren't quite finished here, okay? And then the last part, the last equation, could we use that fourth equation, this one? And so if my displacement is 28.54, the most I can use, the most distance I can use, 15.28 initial velocity, and 5.18 maximum acceleration. If I plug all those numbers in, I find out that this quadratic gives me an imaginary answer for t. What that's telling me is that this acceleration and this distance is not a possible combination when I'm going at this speed initially. What this imaginary number is telling me is that yes, I do stop before going this distance, okay? But what it doesn't tell me is how much time it will take to stop, which in this case, it doesn't really matter. As long as I stop before this distance with this acceleration, then I know I'm good to go. But you have to understand what the imaginary answer is telling you.